Okay, I think we should be good here to be live. And we should have that. Okay. So, welcome back again to another live stream. This will be the 9th live stream of the channel's history. Today we'll be going over the 2011 AP Calculus free response questions. And so as before that we have done many other times, we'll be going through 2 problems at a time. And we'll be looking to see what the solutions will look like as we go through each one. And so with that, we should have exactly what we need. Again, going 2 problems at a time through the answers of each response, which will be recorded and can be seen through the VOD that will be recorded on the channel. So, as we've done many times before, I'll be copying down what we have on this packet onto the notebook and answering each part of the problem. Okay. So as always, all other questions can be submitted through the live chat or through the email over there on the left-hand side, the labcoatmath@gmail.com. And so with that, we should have everything we need to be going through. The first 2 problems, of course, through every packet will be a section that allows for the use of a graphing calculator, and we'll be going through that on each part. So to begin, let me go ahead and copy down what is on problem number 1, and we'll see to it what we can do. So it says here for question number 1 that we have for the interval of the time going from 0 to t to 6, a particle is moving along the x-axis. And then the particle's position x of t is not explicitly given. Okay. But we have the velocity by v of t is equal to 2 times the sine of e raised to the t over 4 plus 1 on the outside. And they also say that the acceleration is given by a of t being equal to 1/2 e raised to the t over 4 times the cosine of e of t over 4, and the original point x of 0 is equal to 2. Okay, so yeah, the camera should be able to focus on that quite easily. Okay, so we have these 2 equations, so let's go over to problem number part A. Is asking, is the speed of the particle increasing or decreasing at time t is equal to 5.5? And we need to give the reasons for that. Okay, so first off, that if the question is asking for speed, of course, our minds will go immediately over to what that exactly means for us when a question is asking for something like that. Or of course, if we have 2 scenarios, a speed up versus a speed down, or I guess more grammatically is going to be slow down, the methods in which we will be able to determine that is going to be with a speed up being that the velocity and the acceleration, again, is both positive or both negative. Right? So mathematically that'll show that the speed of the actual particle, regardless of the regardless of what's happening in terms of that speed, is going to be the situation with that. Okay, and then alongside that, with a speed down for this, a speed down will then be implied with the velocity and acceleration having different signs, right? So if either one is positive, one's negative, or the other way around, that'll be the situation for that one. Okay. And so because of that, then we need to describe what that looks like in terms of the problem itself, right? So at time of 5.5, we can then look at in terms of the velocity 5.5 seconds and the acceleration at 5.5 seconds. Okay, so we just plug that in. So it's 2 times the sine of e raised to the 5.5 over 4 plus the 1 on the outside. Okay, and then for the acceleration, we plug that in as well. So 1/2 e raised to the 5.5 over 4 times the cosine of e raised to the 5.5 over 4. Okay, so with that, we can then get the resulting velocity and acceleration at each of those times. And so we will be able to see what that will look like for this problem. So from this, we should be able to put that straight away into our calculators here, as this is a calculator section that will be allowed. So doing 2 times the sine of e raised to the 5.5 over 4. So all of that with 1 added to the outside. So this will give us the result of negative 0.453 to the 3 decimal places. And the same will happen for the acceleration, where we need to go ahead and do the 0.5, which is the 1/2, and then we will multiply that with the e raised to the, and that's the wrong one, it's the e raised to the 5.5 over 4, all of that multiplied by the cosine of e raised to the 5.5 over 4 again, inside there. Okay, so that is simple plug-in from the acceleration equation, which will then be negative 1.359 rounded there. Okay, so because of that, we have both of them ending up with a negative sign. Again, both of them are negative in terms of that. So we can then conclude that the particle is speeding up at the 5.5 second mark. Okay. So our work shows for itself as to how we concluded that, again showing that we understand that speeding up means that they're looking for either the same signs of both the velocity and acceleration being positive, or in terms of slowing down as the velocity and acceleration having different signs of positive and negative. And so with our work, we can conclude that it is indeed speeding up at that exact time. Okay, so part B then says find the average velocity of the particle from the time period of 0 to 6. Okay, so average velocity, that's going to be our lovely average velocity equation, which should be memorized by this point. So there's the average value of a function, again, is going to be 1 over b minus a, those limits of that integral going from a to b for that function that is in question for us. So with this being the generic equation that is memorized for the average value, if we are looking to find average velocity, again, this will be 1 over 6 minus 0 from 0 to 6 for that velocity function in respect to time. Okay, so what we will then put inside of our calculator, as that was the time frame that they're looking for, will be 1 over 6 from 0 to 6 for that velocity function of 2 times sine of e raised to the t over 4 plus 1 on the outside dt. Okay, so with this will go directly into the calculator, and so we should then get the average velocity as a result. And so let's see what that looks like. So from our calculator, we can then go ahead and put in the function integral, at least on my TI-83 plus, that's what I have right there. So the function integral of 2 times the sine of e raised to the Now we can use the variable t in this case, as we're taking this integral, t over 4. So all of that plus 1 on the outside, and we are integrating this in terms of the variable t, going from 0 to 6 as the limits. Okay, so everything is explicitly stated in terms of that function integral operation, and so the calculator will then spit out for us a lovely 11.696. Okay, as a result of that integration. Okay, now this will, though, again, something to keep track of if you're to keep track of our work, that was just the integral. And so one thing that I just caught myself is that we need to divide this by 6, as that 1 over 6 coefficient is still important. So the average velocity as a result of taking care of that 1 over 6 is then going to be the 1.949 as a result. Okay, and that is just the complete plugging in of the average value function, and we end up with that as our answer. Okay, going to part D, it then says find the total distance traveled by the particle from t is equal to 0 to t is equal to 6. Okay, so total distance, now that means that we have to keep track of the fact that if we then just did the integral from v of t of dt, again, this is just net distance. Okay, in terms of physics, we like to call that displacement, right? So that's just the difference between the start and finish time of that particle, which is not good enough for us. We actually want to have this to be shown as the total distance, including all the negatives as well. Okay, so any other distance that we go in the backwards direction counts towards this as well. So because of that, if we want total distance, that means we need to go from 0 to 6, that time frame that they told us at the start of the problem, but it will be the absolute value of that velocity function in respect to time. This is going to be total distance. Okay, so with that, we can then go plug that right into our calculators, going with the 0 to 6 limits of the absolute value of 2 times the sine of e raised to the t over 4 plus 1 on the outside dt, all still within the absolute value. That will be what is needed to plug inside of our equation in our calculator to get the total distance. So let's have a look at what that looks like. So with the function integral operation on my calculator, if I then go move over and tell it to do an absolute value, we can then plug in for the function of 2 times the sine of e raised to the, it's going to be the variable of t over 4. And so all of that with a plus 1 at the outside of that, closing off the absolute value, then going this time from the integral of t, going from 0 to 6. Okay. So with that, it will crunch through what it is looking for here. Takes a little bit longer because an absolute value will kind of throw in a wrench for the calculator, but should be no problem to solve, as we just need to wait for this guy to come out. Okay, so we get a total of 12.573. Again, that's the total distance traveled by the particle. Okay. All right. So with that, we can get to part D, the last part of this question here. So it says that for the interval from 0 to t to 6, the particle changes direction exactly once. Okay. Then it says find the position at that time. Okay. So that's very good. So with that, that gives us a little bit of clue. Again, the changes direction. Again, what that would mean for us mathematically is that the velocity function, again, needs to cross the x-axis. Okay, and again we're going from 0 to 6 as the time interval for that. Okay, so we can very easily just graph that onto our calculator to look exactly where that happens, where we cross that axis to change the direction for this. Okay, so we can then go to our graphing function for this calculator and take a look to see what that curve looks like. So we can plug in that velocity function of 2 times sine of e raised to the x over 4. We have to change it to x because we are graphing on the xy graph. And let's make sure our window is set, going from -1 to maybe +7, which will show that. Going from -1 to 5 should be fine. We're only really looking for the change, but maybe if we do -5 to +5, we can get a nice window here. Okay. So with that, again, we see this curve and it curls downwards like that. Okay. So there is indeed a point in which that velocity crosses the axis, indicating a change in direction. So let's go ahead and look for that 0, which the calculator can help find for us. So on the left side of that cross all the way to the right side of that cross, we can then tell the calculator and it will give us back the response of 4.579. Okay, so at t is equal to 4.579, again, that is a change in direction according to the calculator. And so with that, we then need to still find the position. We're not done yet because we need to find the actual position of that particle from that. Okay, so of course, in this case, if we then use the fundamental theorem of calculus to help decipher this, again, that shows that if we go from 0 to 6 over, instead of 0 to 6, we can actually change it instead from 0 to the 4.579. So that exact crossing of the axis. If we took that of the velocity function, that also means that we are doing this for the difference, thanks to fundamental theorem, of the position at 4.579 minus the position at 0. Okay, a nice understanding of what definite integrals really mean mathematically. So because of that, we can then isolate for the the position that is of 4.579, which is what they're looking for. So because of that, we can then have that equal to x of 0 being added to the other side of the integral, which can be plugged into the calculator. So the velocity function of 2 times the sine of e raised to the t over 4 plus 1. Okay, so because of that, in respect to time, we then can have everything isolated and solved for the position right at the time at which the particle has changed its direction. Okay, so with x of 0 already being given as 2 from the start of the problem as a nice starting point that they gave us, again the x of 0 being equal to 2, we can then go plug this all right into the calculator and see what we result in. Okay, so because of that, we can keep the 2 plus on the outside of that additional point. Then we can run the integral of the 2 times the sine of e raised to the it's already raised to the, again, we can go back to t over 4 as the variable. Okay, and all that plus 1 on the outside. Now again, this is going for the variable of t, not y, of t, going from 0, this time to that time in which the direction changes happen, so 4.579. Okay, so it's yelling at me for something here. T to 0 to 4.75. I think I'm missing, because if that's closes the e, closes the sine. What exactly would be the problem here? Because we have 3 openings, 4 openings. So t, the sine. Oh, and then, oh, the exponent. Okay, yeah. So we have to insert one more parentheses. Yeah. Alright, a very classic parentheses issue, but with that, that will be exactly enough to put this through as the position of 13.826 as the result when it changes direction at that time. Okay. So just a little bit of calculator mumbo jumbo we had to go through with the parentheses, but with that, that will be how we can use fundamental theorem of calculus to isolate for a position at a very specific time, which we found on our calculators. So that will do it for problem number 1. So we can move on to problem number 2 and see what that looks like before we go ahead and try to correct this. So we've got a few things going for us here, where we have a table here that it's in t in terms of minutes. And we have h of t in degrees Celsius there. And this table contains data points of 0, 2, 5, 9, and 10. Okay. So with that, we have temperatures of 66, 60, 52, 44, and 43. Okay. So it says here that for problem number 2, as a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for 0 to t to 10, where the time of t is measured in minutes, and the h of t in degrees Celsius. Okay, and so they show that in the table that is already up above. So let's go over to part A here, where it says here that we need to use the data to approximate the rate at which the temperature of the tea is changing at time of t is equal to 3.5. Okay, so with that, we have ourselves a very easy, I would say, moment right here, where again it's looking at an approximation of the rate at which the temperature is changing. Okay, so if you're approximating a rate of change, right, of the temperature, so again, if h of t was already described as the temperature, right, again, the approximation of the change in h of t will be very easily described as the simple equation. Again, if we're doing at time of 3.5, we can choose 2 points here, which will encompass that 3.5 very easily for us, which can be seen here as between 2 and 5, where 3.5 is right in between those 2 points. So that's going to be given as the average rate of change equation of h of 5 minus h of 2 over 5 minus 2. Okay, so that is how we set up for that approximation. So we simply have to plug everything in terms of the points on the table, all divided by 3 from there. So we will then get a negative 8 over a positive 3, and this will be in degrees Celsius per minute. So negative seems to be a fine result for this, as we can easily see that the temperature of the tea over time will decrease, again, as it is cooling down. Okay, so a rate being a negative number like negative 8 over 3 does match accordingly to what we have here. Okay, so let's go over to part B here. It says that if we are using correct units, explain the meaning of the expression 1 over 10 multiplied by the integral from 0 to 10 h of t dt, okay, in the context of the problem. Okay, then it says use a trapezoidal sum with 4 subintervals to estimate that expression of 1 over 10 from 0 to 10 of h of t dt. All right, so with that, we have ourselves a little bit of a few steps to deal with. First off, of course, explaining what that is in of itself, which, given how this has been set up, this is a very easy way of saying that the expression 1 over 10, 0 to 10, 10 of h of t. Again, this is set up exactly the way for the average value of the temperature function h of t measured from the interval of 0 to 10 of t. Okay, so mathematically that's just all that really means for ourselves. Because of that, again, structured exactly in the way that average value is meant to be done, with the coefficient of 1 over the b minus a, as shown with the 1 over 10 multiplied by the integral of that function. So with the trapezoidal sum next in our list for us, trapezoidal sum, again, we are going to need to do in terms of trapezoids here that it is going to be the average of the two heights, and then multiplied by each of their bases as a result. And so the area of a trapezoid is going to be just the height of the 2 points divided by 2 multiplied by its base. Okay, so with that, we can get this easily set up here, as the sum is then going to be split up between all these parts. So our first is going to be 66 and 60 as the 2 heights all over 2 multiplied by the base of 2. Then with that, we will then go with the 60 and 52 as the next 2 heights for ourselves. So 60 plus 52 all over 2 with the base of 3 there. And then continuing forth, we have 52 and 44 as the next 2 heights all over 2. Multiplied this time between 5 and 9, that's going to be a base of 4. And then lastly, we have 44 and 43 all over 2. And between 9 and 10, as the last 2 distance of the base will be just a base of 1. Okay, so this can be done by hand, but thankfully, because this is a calculator problem, we can go ahead and consult the use of our calculator here to find all of that out. So we get 66 and 60, all this divided by 2, multiplied by the base of 2. Adding that with all of 60 and 52, all divided by 2, multiplied by the base of 3. And then we have the other one of 52 and 44, all divided by 2, multiplied by the base of 4 there. And then our last trapezoid, that is, of 44 and 43, divided by 2, multiplied by the base of 1. Okay, so with that, all of them are shown to be all added up to a total area of 529.5. Okay, but again, that was just the sum. Again, we need to know the actual 1 over 10 multiplied to that sum. So for us, that will just move that decimal point back one. So that's 52.95. Again, in terms of the average value, again, that's degrees Celsius average for that function h of t. Again, going from 0 to 6 on the interval of time in which they asked us to calculate for. Okay. So with that, we have truly understood what they're asking for if they looked at average value of this type of function, and we end up with something like that. Okay. So we can then move forward to part C. It says here that we want to evaluate. Now this time, the integral from 0 to 10 of h prime of t dt instead. Okay, and then we want to use correct units to explain the meaning of the expression. Okay, in terms of the problem. All right, so h prime of t, again, that integral then, okay, of the 0 to 10 h prime of t dt. Again, this is going to be that change between, if we're using fundamental theorem of calculus, right, so h prime of t dt, again, using fundamental theorem of calculus as shown, we then are going to take this problem back a step from the derivative after taking its integral of h of 10 subtracted by h of 0. Okay, and in this case we can run the evaluation ourselves because we do have each of those points of h of 10 and h of 0 listed for us on the problem itself. So that's going to be 43 minus 66. Okay. So as a result, this is going to end up as a negative 23 as a result. But that negative 23 has units of degrees Celsius, as both the h functions are talked in terms of degrees Celsius. So because of that, we end up with the negative 23 degrees Celsius as a result of that integral that we just had. But in terms of what that means for the expression, again, this means that this is the net change in temperature of the T from 0 to 10 minutes. Okay, and I realized that my previous problem, I was still stuck on the last time interval. It should be 0 to 10 on that, because that's the total time difference that we are looking at for the T. Okay, so that's what the explanation is going to be like if we then took the integral of the derivative of h of t, ranging it from 0 to 10 in that way. Okay, so with that, we can then go to part D here. It says that at the time is equal to 0. Now biscuits, it's like almost we're in England, but biscuits and tea, that's not how the way we do things here in America. But it says biscuits with temperature 100 degrees Celsius removed from an oven. Okay. The temperature of the biscuits at time t is modeled by b, let's see, yeah, so modeled by the function b, for which b prime of t is equal to negative 13.84 times e raised to the negative 0.173 times t on the exponential plot, okay, is no. Okay, so it says here using the given models at time t is equal to 10, how much cooler are the biscuits than the tea? Alright, so we've got ourselves quite the problem here, because we have another type of function here that they're throwing in here that we have to compare between the biscuits. So we already know that h of t, for this is for h of 10, that is for the t at the 10-minute mark, was already 43 degrees Celsius. So we can leave that off to the side as something that we can review back later. But then we only have b prime of t given to us, right, as the function that they stated back there. But we also know that if we have b of 0, so for the biscuits at time of 0, they exit that oven at 100 degrees Celsius. Okay, so we then need to find b of 10 as something that we do not know yet, as an actual temperature function of the biscuits on their own. Okay, so thankfully though, we can use good old fundamental theorem once more, so I'll abbreviate that as FTC, as given that if we do take the integral going from 0 to 10 of the derivative of the biscuits function that we already have on the side there at the start of the problem, that is going to be that net change from b of 10 minus b of 0. Okay. And then taking back a step from taking the integral of a derivative of a problem, So from that, we can isolate b of 10 as being the b of 0 added to the other side of the equation from 0 to 10 of b prime of t dt. Okay, so we already know b of 0 as 100, and we have the integral already because the derivative function was already explicitly stated for us as that negative 13.84 multiplied by e raised to the negative 0.173 t dt. So again, all of this can be thrown right inside of our calculator, and we should be able to find the result for that biscuits at the 10-minute mark that they were asking for. And so with that, we can then rush to our calculator here. We can keep that 100 plus on the outside for that original b of 0 point that they were talking about. Then if we were to take that function integral for the exact equation that they gave us at the start of the negative 13.84 multiplied by e raised to the negative 0.1736 multiplied by that variable of t, and we've copied exactly what that function is going to be like. Then we tell it that for that variable of t going from 0 to 10 minutes, as was the time interval described, we then result with a temperature of 34.326. Okay, so b of 10 is going to be 34.326 degrees Celsius. All right, so for the comparison of the tea at 10 minutes versus the biscuits at 10 minutes, of course, we can very easily see that the tea, not the tea, but if they're asking for which is actually cooler at the time, right? The biscuits are cooler than the tea at the 10-minute mark. Okay, so we have all of our work showing for it, at least how we could reach that comparison between those two different functions. Again, using good old fundamental theorem of calculus to be able to prove that, given they only gave us the derivative of b with an initial point of 100 degrees Celsius. So with that, that should conclude what we have for the first two problems on this packet out of all 6 of them. So with that, I will actually be transitioning back to the answer key to see how we performed on these first two problems. So we'll go back to the first problem here that we've done earlier. And just to show what I am looking at on screen when I compare these two, we have ourselves, if I show this monitor here, that we do have the 2011 AP Calculus, again the scoring guide, and we'll be going over it once I complete every problem on our own to see how that matches up with what we have on our notebook. Okay, so with that, back to what we have here from all that we've calculated so far. Going to the first problem here, and we have that particle that's moving across. Part A is that if they're looking for a speed up or a slow down for the particle at the time, okay, we say that the particle is indeed speeding up because both the velocity and acceleration, so again that was the velocity at the given time, that's the acceleration at the same time, with them being concluded that they end up with a negative on both of them, right? They have the same sign, so we can conclude that the particle is indeed speeding up at that time. So with that, we will then show that it is speeding up, and that will grant us both points, 2 out of 2 correct for this part. Okay, then going over to part B here, they want to do the average velocity, which will be set up as that exact function of 1 over 6 as the coefficient of 1 over b minus a of the limits of the velocity function as shown. Throwing that right in the calculator, getting the 1.949 as shown was exactly what we needed. And so because of that, we get both points correct of our setup and our answer that they were looking for to find the average value of the velocity function for the particle. Then moving on to part C here is that we have the total distance. Again, that's what they're looking for that part, meaning that you had to set it up as the absolute value of the velocity function inside of the integral. Again, total meaning that you take the absolute value, meaning all the negative values for the distance is going to be swapped back to positive. And so by plugging that back into our calculator, ending up with 12.573, as shown right there, is exactly the answer that they were looking for. So both the setup and the answer again are going to be both 2 points out of 2 for this section. Okay. Then for part D, we have ourselves the looking for that time in which we change the direction. So again, I think I still have it actually here as part of the graph. Because we have the velocity function that was given for the particle, by plugging that in directly into the calculator, we can see that there is a change of direction at a specific point that you can calculate for by crossing the x-axis. And so by doing that, the calculator spat out the 4.579 as a result of that change in the direction. So because of that, we can then go put in for the fundamental theorem of calculus again, up until that change of position, the change of direction for the particle. By doing that, we end up with the difference of those two positions. We did isolate for the position that they were looking for, the 4.579. So by running it through, we do end up with the final result of that for the 13.826. Okay, so because of all of that running through there, okay, we then end up with the actual result of all 3 out of 3 correct for this part. Okay, very good. So with that, we get 9 out of 9 correct for this first problem. So what I'd like to do to make my lives a bit easier, because we do calculate how much total points we do get at the end. So question 1, 2, 3, 4, 5, and 6. With the first one being 9 out of 9 correct, again, we will grade this out of all 54 available points, as each question is graded out of 9. Okay, so that's pretty good to start out with. So that will be it for question number 1. So for everyone that is watching again, all of the questions that you might have and any math subject related can be sent directly to the email of labcodemath@gmail.com, again shown over there on the left side, or anything through the live chat would also be responded to if we have any questions according to that. Okay, so with that, we can go over to question number 2 here of that question that we just went over for the tea that is cooling down in comparison to those biscuits at the end. So again, question A was asking for an approximation of the rate of change for the temperature. Again, that is just going to be a very simple rate of change, average rate of change equation that we have, the h of 5 minus h of 2, all over those two different time differences. So ending up with a negative 8/3 degrees Celsius per minute was exactly what they needed. So this was just a single 1-point question correct, as the students will understand what average rate of change really looks like in terms of this problem. Then going to part B, we're looking for then, they gave us that expression of the 1/10 multiplied by 0 to 10 of h of 10 dt. They asked for what that really meant in terms of the problem. And so of course, with what we just did right in the previous problem of this being the average value of the h of t function, we just need to state that accordingly. That from 0 to 10, that is going to be the average temperature of the t from that time frame. And so with that, we can then go with our trapezoidal sum of all of this being thrown in there. Again, trapezoids, of course, being measured by the area of the two heights over the average multiplied by the base. We had the 4 sub-intervals that they were asking for that were very easily calculated across the table value. So again, it's 2 heights multiplied by the base, so how far they went across each of those trapezoids. And so because of that, all 4 of them were all added up in accordance to that. And so by us then taking the actual approximation of the integral from that 0 to 10, and then multiplying by that very easy coefficient of 1/10, we then end up with the average value of that h of t function as 52.95. Exactly what they were looking for. So by us showing that we understood what the expression itself did mean in terms of the problem, then of course the actual trapezoidal sum being set up properly, all 3 out of 3 is going to be correct for part B. Okay. Then for part C, we have ourselves then the next part where they're looking to evaluate what that meant for the h prime of t taken inside of the integral from 0 to 10, and we need to show which correct units that was going to be. Thankfully, of course, with our full understanding of fundamental theorem of calculus, of what it means to take an integral of a derivative of a function, that will just mean that we revert back to the original function h of the two different intervals, again, of the limits from h of 10 minus h of 0. So because of that, we then just easily refer back to the table of values, because those are direct points that were provided to us at the start of the problem. So by taking that difference, we end up with a difference of negative 23 degrees Celsius. So that was indeed going to be correct for the value of the integral. But then, of course, what that meant in terms of the actual problem itself is that by taking the difference between the 10-minute mark and the 0-minute mark for the temperature of that T, that was going to be indeed that change in the drop of temperature as we go from 0 to 10 minutes. So that evaluation was also correct. So that is going to be 2 out of 2 correct as well for this for this part C of this problem. And lastly, we have this segment of looking at the temperature of biscuits now in accordance to the T. But unfortunately, they only gave us the derivative of that temperature function, B prime of T, and one original point with the biscuits starting at 100 degrees Celsius at time of 0. So once more, they're testing us again, understanding what the fundamental theorem of calculus is really going to be. Okay, so because of that, we then realize that by looking through these two different points here, that we can set up the integral of b prime of t as shown right there, as that will be similarly to part C, the difference between the 2 points of the biscuits at 10 minutes minus the biscuits at 0 minutes. So because they gave us b prime of t, this we plugged right into the integral itself. Again, that can give us an answer from the calculator. And because b of 0 was given as the original temperature of the biscuits right when they come out of the oven, we can then set up the entire equation to solve for the biscuits temperature at 10 minutes. So the calculator gave us that response of 34.326 degrees Celsius as a result at the 10-minute mark. And because of that, the h of 10 is going to be the result. So indeed, the biscuits are indeed cooler than the T itself. So that will give us all 3 points for this part. Very nice. Okay. So that will be 9 out of 9 correct. And I am getting phone messages at this time. I'll make sure to silence that off. But so all 9 points were awarded to us again right here. And our friend Nicholas again says that it is indeed another day, another math problem. Yes. And thank you as well for tuning in to the live stream. I know there will be plenty of people that might find this quite interesting to see, as we have actually are getting very close to breaking our record of getting on our way to hopefully getting all 54 points correct. We still have not managed to do that yet in the history of this channel, so we can definitely see what that looks like once we complete all the problems. But with that, we are well on our way to getting to these next parts of our stream here. So that is the first 2 problems done. Now with the next 4 problems, so problems 3, 4, 5, and 6, which for whatever reason my camera decides not to focus here. Do you mind? Hello? Let's see. Come on. Yeah. Okay. So with problems going from 3 all the way to 6, so the remainder of this exam, this will be a no calculator section. So again, the calculator that we've been using all so far is going to be put away here, as these last sections, for again going from 3 all the way to the end of the exam, all the way to 6, will not require a calculator. Okay. So let's go over the next 2 problems together, and we'll see how our score holds up. Okay. So going over to problem number 3 here, we have ourselves the graph shown here. So we get all the way to 1 over there. So we have one curve going here, and then we have another curve going there. Okay. And the intersection point, they give us the coordinates of 1/2, 1 as the result of that. Okay. So it says here that for the problem that let R be the region in the first quadrant. Okay. Enclosed by the graphs of f of x is equal to 8x to the 3rd power and g of x being equal to sine of pi times x, okay, as shown. Okay, so with that, we have the graph, we have the problem, so let's get over to part A to see what they are asking for. Okay, so it says here to write an equation for the line tangent to the graph of f at x is equal to 1/2. Okay, so if we want a line tangent to a graph, again, that graph of f, that will then mean we were going to need the first derivative graph equation, that is, of f, in order to find the slope of that line tangent. Okay, so because of that, we have the function of f as 8 times x to the third power. So that derivative using good old exponent rule will give us 24 multiplied by x squared as the first derivative of f. And so because we're doing it at the exact point of x is equal to 1/2, we will then find for f prime of 1/2, that is going to be 24 multiplied by 1/2 raised to the second power. So using good old order of operations, we need to do the exponent first. So 24 multiplied by 1/4, meaning that we have a resulting 6. Again, this is going to be the slope of the tangent line. Okay, and so if we want to find the equation of the tangent line, we need not only just the slope, but we need the entirety of the function y is equal to the slope that we already have of x minus h plus k on the outside. That's the form, at least in the point slope form, that the AP graders like best. So we need to find h and k. Again, this is going to be the point of tangency, is the fanciest way of saying where in that world is that point in which that line is going to cross the function. Thankfully, with x is equal to 1/2, they already gave us that point as part of the function. So again, the point at which that line is going to cross is that 1/2 comma positive 1. Again, this could be easily found as well if we plugged it in to the original function of f. So with that, if we really wanted to prove it, again, it's 8 multiplied by 1/2 raised to the third power for the original function of f. So with that, that'll be 8 multiplied by 1/8 as a result of 1/2 being raised to the third power, which is also a positive 1. So it just proves that that is indeed the point in which it will cross. So because of that, we can then plug everything in, the slope of 6 that we've already found earlier, x multiplied by x minus the actual value in which it crosses of 1/2, plus the y value of 1 on the outside will give us the entire equation of that tangent line. Very nice. Okay, then part B will continue that we need to find the region, the area of the region R. Okay, so again, R was that region enclosed by both of those functions. So because of that, if we were looking to find the area matched between two different curves, what that means is that we need to go, and so the area for us is going to be the entirety, again, going from A to B, so where those two of them end, but the main idea here is that it's going to be the top function subtracted by the bottom function. Okay, and so by doing that, again, we are removing everything that's underneath the bottom function, so all of this is being taken out, while everything over here in the section of R, which I can try to use a different color here to show that. Let's try my green pen here. So everything in the region R underneath the top function will all be calculated in, and so we get the total region of R in which we see right now. Okay, so because of that, we need to understand which function is the top and which one is the bottom, right? So which of them, again, is going to be the one that actually is going to be going above the top and which will be going underneath the bottom. For those who understand what we're looking at least in terms of the two functions of sine versus 8x to the third power, right? We can go one of two ways about this. First, of course, with the sine function, right? Again, any sort of sine function without any other crazy coefficients in front of it, the sine function looks something like the starting wave. Again, starts at 0, curls upwards and then downwards like that. While on the other hand, the x to the third function, again, being in terms of x raised to the third power, is going to have that lovely curve upwards like this. Again, the concave up starting upwards like that as a result. And based off of intuition, if that will be enough for some students, again, this will be where the g of x is going to be the top function, while 8x to the third will be the bottom function. But if we actually wanted to find a bit more mathematical proof behind that, again, something to note is that if you look at the way this goes, that the function that is on top, again, that's going to be a concave down. As a result, again, this curls on the downward scale of what we're looking at right there. While, of course, the other function curling upwards like this, that's going to be a concave up, right? So if we were to mathematically prove about ourselves which one's going to be top or bottom, if we want to look at concavity, again, that curvature of the function, that means that we have to go take the second derivative of both functions f and g to prove to ourselves that we are looking at what this looks at, proving what we're looking at in terms of both of these guys. And we can also use this if x is equal to 0, of course, being the starting position where the concavity begins for each of them. Okay, so because of that, if you want to look at concavities and the second derivatives, that means that the first derivative of f, and we run that through, as 24 as x squared. That was already done earlier in the previous problem. But if we want to take its second derivative, so by going one more time, we are going to get 48 times x as a result. Okay, so with this, again, any sort of value, again, going up to 1/2 there. So again, at x is equal to 1/2, right? So f double prime of 1/2, that's going to be a positive value, right? In this case, it was going to be 24. So this is the concave up function. Again, the one that goes concave up, curling upwards. So that does show that it is the bottom function between the two. But then if we wanted to show that for the function of g, the first derivative of g, that in itself, again, by running it 2 times, the first time we get it as the positive cosine of pi times x. Now with the chain rule, we multiply with a coefficient of pi waiting on the outside. But by running it one more time of the second derivative of g, we can leave that coefficient out there one last time as a pi. Now we go a negative sign of pi over 6 as the derivative of cosine will result in that. And with another pi leaving from chain rule, it's pi squared as a negative coefficient waiting on the outside of sine. Okay. So because of that, if we were to choose that x equals 1/2 at that point in which they both intersect on each other, then that would mean that g double prime of 1/2 will be negative pi squared multiplied by the sine of 1/2 times pi. So again, sine of pi over 2, as something that should be memorized from the unit circle, is going to be a positive 1, meaning that the second derivative of g is negative pi over 2 pi squared at that point. Again, proving that it is a concave down function. Okay. So with this little bit of extra work, we have indeed proven to ourselves that we are looking at a concave down function. So because of that, we know exactly which one's going to be on top and which one is going to be on bottom. So because of that, we can finally get the area set up between these two. Again, thanks to the intersection already being shown at x is equal to 1/2, we will then go from 0 to 1/2 as the limits of our integration. Then going for the top function, g of x, that was shown, subtracted by f of x, the bottom function, dx, as the mathematical area between those two functions. Okay, so because of that, we can then plug in for everything that we have here. So 0 to 1/2, and g of x being shown already to ourselves at the start of the problem as sine of pi times x, subtracted by f of x as 8x to the third power dx. So this integration should not be very hard to be done by hand. Again, this is a non-calculator section for ourselves. So because of that, we can go run this integration as a negative cosine of pi over 4, remembering that the integral of positive sign gives us negative cosine as a result, and the chain rule resulting in 1 over pi as a coefficient to match the pi that's going to come out of the differentiation. And then we subtract that then with 8x to the third power, meaning that we have to raise it to x to the fourth power, and leaving a 2 coefficient will match the 8 that comes out if we ran the chain rule back from the exponent of 2x to the fourth power, and we evaluate that from 0 to 1/2. Okay. A fairly simple integration done by hand, which from there we should be able to then follow up to see what this looks like when we run the limits of integration. So the first part being negative cosine of pi times 1/2 times 1 over pi waiting on the outside, subtracted by 2 times 1/2 all raised to the 4th power. All of that, so that's all the top limit evaluated. Now we need to go evaluate for that bottom limit. So we subtract it by all of the negative cosine of 0 times pi times 1 over pi, subtracted by 2 times 0 to the 4th power. Okay, so we plugged in for both limits, and so now we just need to run the actual math here in this of itself here. So with this being cosine of pi over 2, cosine of pi over 2, again, thanks to the unit circle memorization that we have already, this will go all to 0 for this guy right there. Again, cosine measuring the x value of that part of the unit circle. 1/2 raised to the 4th power will be -2 multiplied by 1 over 16 as a result. Okay, so we'll keep that there. And then we keep the subtraction now. Cosine of 0, again, this cosine of 0 as a result of 0 times pi is going to be a +1. So it's going to be negative. Now we keep that 1 multiplied by the 1 over pi as a result of that multiplication. And of course, 0 raised to the 4th power is going to be just all 0 for the rest of that. Okay, we have a lot of negatives to keep account of, but that should be no problem for ourselves just to handle on our side here. So that's going to be -1 over 8 on one side, adding with a 1 over pi on the other side with the negatives factored in. And this will actually be the area that we are looking at, okay, as a result of those two. Okay, then going lastly to part C here, after all of our wonderful integration that we've just done by hand. It says here on part C that we need to write, but do not evaluate, an integral expression for the volume of the solid generated when R is rotated about the horizontal line y is equal to 1. Okay, so we've got ourselves a very interesting situation right here where we're looking at the actual rotation of the area itself of R. So just to make sure we're on the same page about this is that if we have the resulting area R, again the intersection being 1/2 comma 1, again if we're looking at the horizontal line y is equal to 1, we go across this line right there, and they're saying to rotate it about that way. Okay, so because of that, this will actually change the way that we're all going to look at this integration, meaning that it's going to be the distance instead from the x-axis shown at the bottom. Again, it's going to be measured the distance from the actual parts, again furthest away from the y is equal to 1 line. And as you can see, there's two different spots which they will be rotated, so that will be basically a big R minus a little r for a volume rotation. Okay, something like this, which I have made a few videos about latest on what I titled as the hardest part of AP Calculus. Again, meaning that we have to set this up as a volume function, meaning that it's going to be the going from A to B for this, again now as the difference between two different revolutions being subtracted from each other. So that's going to be pi on the outside, because the idea being that we're doing pi r squared but integrating it and turn into an actual volume. So that's the large radius squared subtracted by the small radius squared. In this case, dx, because we are measuring vertically across that line of y is equal to 1. Again, shown right there, that we are rotating about. All right. So because of that, we have everything that we need to start looking into this. So being that we have big R to solve for, again, that is going to be the distance from the line of 1 all the way down to the furthest function, which we've already proven as f of x, right? That being the function down there. So instead of just calling it just f of x, because that will be incorrect, again, we are looking at the whole distance of 1 all the way down to f of x. Okay, so because of that, by understanding what that looks visually, if we took the whole section of 1 and subtracted it away from those values of f of x, we climb closer and closer to the point of 0, because we match it with y is equal to 1 on that side. So if we show that the large radius is 1 minus f of x, that will properly show what it looks like to reach that curve on the further side of the y equals 1 line. Okay, and then our friend Nod here says u is equal to 943. Yes, I have no idea what you're talking about. You might need to clear that one up for me if you might. Okay, so with the 1 minus f of x right there, we can easily substitute that back in as 1 minus 8x to the third power. Okay, and then we need to go with the smaller radius now as the distance from the y equals 1 line all the way to the nearest side of the top function, which was already described as g of x from our previous work. Okay, so the same fashion there, that it's going to be 1 minus instead of the f of x, because we're measuring the distance from the line of 1 all the way down to the g of x function. That's going to be 1 minus g of x. And that was going to be substituted back as 1 minus the sine multiplied by pi times x. Okay, so with that, we should have everything that we need here to start putting this all together into that volume expression, again, that they want us to evaluate but not to actually solve. To write out but not actually evaluate on that side. Okay. Oh yes, Nado said that he'll show his math later. Yes, why don't you email me, as my email is right there on that left side, to see what that looks like. I might even put that on the screen just to see how much better of a mathematician you are than me. I think that'll be a great piece of content, wouldn't you? But with that, we can then just easily substitute everything in, and so the volume expression that they were looking for us to write down is that we will take pi as a coefficient on the outside, and then we evaluate it again in terms of dx by all the way to the point of x being 1/2 as the limits of the integration. And then we do the big R squared that we've already found earlier. So it's 1 minus 8x to the third power, all that squared, subtracted by the little r squared right there as 1 minus sine of pi x that we've shown right there, all of that squared dx. Okay. So with that, that's one way of doing it, and I think in terms of what exactly the test graders are fine with is that if we also just left it in terms of just f of x and g of x, that would be acceptable as well for the test graders, at least in my experience of looking at these types of papers. So either way will be fine. I just like to put it out in terms of the actual raw values of x, so that if you did put this into the calculator, if that were ever asked, all of this will be exactly thrown into the calculator and the actual answer will be spat right out and we will get what we are looking for. Okay, so that should do it for problem number 3, as all 3 parts of this question with that graph involved is going to be asked for. So let's move on to question number 4. Again, any other questions can be submitted straight through the live chat or to the email as we get to problem number 4 before we start grading our next 2 problems that we have done here. Okay, so problem number 4 looks like has another graph, which I will very quickly copy down here. That we go from 4 to 3, 4 on this side, then we keep going to 3 on the right side. Okay, and we go down 3 on here, and we go up 3. Okay, so we start plotting some points here like this, and then like that. It looks like we're right in between there, and then 3 comma, so 3 comma negative 3 is 1 point right there. We have negative 4 comma 1 right there. Okay, so it looks like we curl upwards like this, and then draw a straight line all the way down between those 2 points. Okay, the question notes this as graph of f as a result. So for context here, the problem does say that the continuous function f is defined on the interval from negative 4 going all the way to positive 3 on x. Okay, it says here that the graph of f consists of 2 quarter circles and 1 line segment as shown. Okay, then they give us another piece of information that we want to let g of x, a new function, be described as 2x on the outside plus the definite integral going from 0 to x for the function f of t dt. Okay, very good. So with that, we have ourselves this problem right here that we are looking for in terms of this graph and what is described. I guess my graphing wasn't exactly the best. This is meant to be shown as kind of like a circle business looks like from -3 all the way to 0. But nonetheless, we should have everything we need to start answering the next problem here. Part A says that we want to find g of -3. So it says to find g prime of x and evaluate g prime of -3. Okay, very good. So with that, we have all that we need here to start answering this first part. That we want to find all these 3 points. So g of -3, g prime of x, and g prime of -3. So the first part being a very easy plug-in to the function of g. So g of -3. So that's going to be equal to 2 multiplied by -3 on that side, adding it with that integral, going from 0 to -3 of f of t dt. Now, we don't like going from 0 to -3 because that's kind of going backwards in terms of what we need to see for our definite integral. So, on the other hand, while we can evaluate for the -6 as a result of that multiplication, we need to actually change the way these limits look like on the definite integral by flipping the limits instead to reflect what we want from -3 to 0 of f of t dt, slapping on a negative coefficient as a result of that change in that. Okay? So because of that, we then will get our section right here of -3 to 0, meaning that we need to go for this entire part right here shown on the graph, right? So this is -3 on the x going all the way to 0. Again, this was showing as a quarter circle as was explained on the problem itself. Okay, so because this is going to be the area under f of t, as shown as what an integral really means for us, is that we can leave the -6 out there and we can solve for an area of a quarter circle, right? Again, this being that we are dealing with the quarter circle, again, from from -3 going to 0. Okay, so with that, because we're a quarter circle, we then need to find a radius here, right? Given that a quarter circle's area is pi over 4 times r squared. Again, just slapping a nice 1/4 on the outside of the area of a normal circle. So with that, the radius, of course, of this kind of circle, as we very easily see, is just going all the way across of 3 units along the axis. Will that mean that we have a radius of 3? So it's -6 minus pi over 4 multiplied by 3 squared. So with that, we can evaluate that as -6 subtracted by this time as a 9 pi over 4. And that will just about do it, as those two cannot combine into very easy numbers without a calculator. Okay, so this is going to be, again, this was the evaluation of g of -3 as the first part that they were looking for. Okay, then g prime of x is the next part that they're looking to evaluate for us, which means by taking the derivative of that g function right there that was listed there on the top, we then just go across, so the 2x becomes a positive 2. But then by taking the derivative of this integral right there, so if you want to show that in work, that if we're taking the 0 to x integral of f of t dt, if all of this was having its first derivative taken in according to x, we then need to refer back to fundamental theorem of calculus, showing that by taking a definite integral's derivative, we will then revert back to the original function now of f of x on that side. Okay, so with that understanding of fundamental theorem, we have evaluated for g prime of x. So lastly, we just need to then evaluate for g prime of -3, as that's what they were asking for this part A. So with that, g prime of -3, then we'll have 2 plus f of -3 as shown right there. So f of -3 is just going to be easily tracked right on the graph of -3 on the x part, meaning that we get 0 on the y, so 2 plus 0. So to line that up, g prime of -3 is just going to be a positive 2, that is, on that evaluation. Okay, a few steps for part A, but should be no problem for us to evaluate each of those things that they are looking for. Then going to part C here, part B, I gotta make sure to keep my letters straight here. Part B then asks to determine the x-coordinate of the point at which g has an absolute maximum on the interval, -4 to x to +3, and we need to show as to why that is the case. Okay. So again, if we were looking for absolute maximums along any sort of interval, that would require us to then look at the following candidates. Again, for ourselves, that could be possible results of this type of problem. Okay, so candidates for any sort of absolute maximum means that we need both the endpoints and any sort of local maximums that will be possible as well between the two. Okay, endpoints, of course, being that we need to then look at points g of -4 and g of +3 as possible results again. So we need to look at what those actual values are going to be, and we'll compare them at the end. Okay, then going forth, then with the local maximums, again, that would mean that we need to take the g prime of x and do a lovely number line analysis, as we need to see, according to the g prime function, that a positive value on that derivative function needs to then transition to a negative value crossing the x-axis at a specific x value that we need to look for as part of our number line analysis for that result. Okay, so because of that, we then need to then go back to what we had started in part A, that we already know that g prime of x is equal to the resulting 2 plus f of x. Okay, so with adding 2 to the result, we need to see at least any points in which the f function is going to be -2 to look at where the g prime of x crosses the x-axis. Okay, so with that, if we were looking to see, looks like there's only one point in which the graph of f actually goes to -2, which will be, again, somewhere along that line, which is part of that linear function right there. And we know one point already at 3, -3. So in order for us to find that point, we do need to look at the next point of 0, +3 as a result of that. Okay. So alongside of that seems very odd, at least. No, because yeah, that looks like we actually have a slope for ourselves. So the slope of that line, if you're trying to pinpoint exactly where that point is, where it's going to be some x value, -2 as a result of f. Then from there, we need to again find the exact function, again, in terms of y is equal to mx plus b, at least for ourselves, so that we can then plug in to see where -2 will be on that value of y. Okay, so because that our slope then is going to be the difference between the 2 points at 0, 3 and 3, -3, so that slope is going to be the resulting -3 minus 3 is the difference of y's, and the difference of x is 3 minus 0. So -6 over +3 gives a slope of -2. Okay. So because of that, then we already have the y-intercept. If x was equal to 0, it's going to be +3. So the resulting equation is y is equal to -2 times x plus 3 on the outside. Okay, so now we actually have the total equation of that line segment right there, of that part of the graph of f. We then have everything we need to then plug in for -2 for y. So then -2x plus 3 by subtracting the 3 to both sides of the equation, that the x value is going to be +5 over 2. Okay, so with that, we do indeed show that the graph of g, again, given that we are going from positive values of f into negative ones, again, as f was decreasing, is that this is going to be the resulting at 5 over 2. That is also another possible candidate for us to look at for this evaluation for the absolute maximum of the function of g. Okay, so because of that, we then need to look at each one of these and get to some answers. So if we want to evaluate for g of -4, that's going to be 2 multiplied by -4, adding with the integral from 0 to -4 f of t dt. Okay, so because of this, we can then result that we have a -8 subtracted. Now again, we need to swap those limits around from -4 to 0 of f of t dt. Okay, so I need to stop hitting my camera is one thing, but on the next point here is that we already have done some of the work for this, because we can split this now as the two integrals from -4 to -3, and then also from -3 to 0. Okay, this we've already done before as that from part A, from -3 to 0, as shown right there. So because of that, we actually end up with that -9 pi over 4 as a result of that subtraction of the two. Okay, so -9 pi over 4 is the result of that integral right there. And so with that, we can actually go ahead and go from -4 to -3. So, geez, this camera keeps getting in the way. But from -4 to -3, again, this is going to be another quarter circle. Okay, as was explained in the problem earlier. But this time, it's going to be a radius of 1. So pi over 4 r squared, that's the quarter circle equation. But again, r is equal to 1 in this case. So the resulting g of -4 point is going to be -8 subtracted by pi over 4 subtracted by another 9 pi over 4 as the other quarter circle that we've dealt with earlier. So the actual total value is going to be -8 subtracted by 10 pi over 4. This should be enough to kind of tell us that g of -4 does not seem to have any chance really to be a maximum, but we'll hold that in mind just as something we can evaluate towards the end here. Okay. Then moving forth, of g of +3, that's going to be 2 multiplied by 3, adding with the integral from 0 to 3 f of t dt. Okay, so that being plugged in for that is going to be a +6 added now with, going from 0 to 3 will be this entire section right there. Again, thankfully, we already know that the equation that we've already found earlier of -2x plus 3 still holds for that entire segment that is just made up of that line. So that's going to be the integral from 0 to 3 of -2x plus 3 dx now, as in terms of the x that we're integrating. So that'll give us going from 6 plus the integral being -x squared plus 3x evaluated from 0 to 3. So that'll be 6. By plugging the 3's as the limits will be -9 plus another 9 subtracted by 0 as the last limit of 0 being plugged into both of them, which thankfully those cancel out quite nicely, so we end up with a +6 as a result of g of 3. And lastly, a g of 5 over 2. That will give us the 2 multiplied by 5 over 2, then added with the integral going from 0 to 5 over 2, f of t dt. So with that, we can then evaluate this one last time. So +5 results of the 2 times 5 over 2, adding that with the integral. Again, the same. 0 to 5 over 2 is going to be just exactly this part right here, which is just still part of that line segment that we figured out earlier. So that will give us the 0 to 5 over 2. F of t dt will then give us the -x squared. Sorry, no, let's actually go one step at a time here. So it's -2x plus 3 dx as the actual function of that line. And then we run the integral. So this time it's going to be the -x squared plus 3x evaluated from 0 to 3 to 5 over 2. I need to keep that in mind. That would have been a pretty bad mistake. 5 over 2 was the limit that we're going for on this problem. So with that, it's going to be 5 added with the -25 over 4 by evaluating 5 over 2 squared plus 15 over 2, and then subtracting by the 0, as the 0 limit will be getting both of them to 0. Okay, so 15 over 2 will be transferred to 30 over 4 to make the denominators the same. So that will be 5 added with a 5 over 4 difference right there. Okay, which this actually goes a little bit over 6 because 5 over 4 can be made to 1 1/4 as a result. So 6 1/4 will be the result of g of 5 over 2. So actually, after all of our work here, we can conclude that g of 5 over 2 is going to be the absolute maximum, right, of this function, again going from -4 to +3. Okay, so a little bit of work was required, but we have everything we need to show mathematically that we have done all the work to prove that we have an absolute maximum of the function by looking at all the candidates of both the endpoints of the function at the interval that they are describing, as well as any local maximums that we have shown by taking the first derivative analysis of that problem. Okay. Now, we aren't done yet, although I ran out of space here, is that then we need to go to part C and D here. So part C says that we need to find all the values of x on the interval -4 to x to +3, for which the graph of g has a point of inflection. Okay. And then we need to give a reason for that. Okay, so if a question is asking for points of inflection across a function that they are looking for, of course what that means is that we need to again take the second derivative of g to look at that. Okay, again, at least when that's equal to 0, that's going to be a point of inflection for us mathematically. Okay, so because of that, we then need to go take each derivative. So the first derivative of g is going to be, again, all of it was that 2 plus f of x that was shown previously in our work beforehand. So then by taking the second derivative, that's going to give us a 0 plus the first derivative of f as a result. Okay, so because of that, then we need to see where that second derivative of g is going to be equal to 0. In this case, it also means where the first derivative of f is going to be equal to 0. That also counts as well. So if we're looking to where that first derivative of f is going to be equal to 0, we can look back on our graph here. Okay, I think it might be easier actually to look at the packet itself as a better representation of the graph. Okay, so we have the graph of f that was described earlier, and we want to see where that first derivative of f will then go to 0. Okay, so that's where the slope of f is going to be equal to 0. For at least for us, there's going to be, it looks like just one point where that is going to be the case at x is equal to 0. Okay, so because of that, again, by showing that we have the change from a concave, this is the first way. So we have an increase again. So the change, so the increase on f to a decrease of f. That's going to be, again, as you see, right, we are increasing, going up in value, and then going down in value after f of 0. That's going to be the only case in which we have a point of inflection, right? So f prime of x is equal to 0 at x is equal to 0. So that means that the g del prime of 0 will be 0 then. So g has an inflection point at x is equal to 0. Okay, again, showing that, again, f is increasing, then decreasing at x is equal to 0. Okay, so we have shown that we only have one point of inflection at x equals 0 after reviewing what we have on the graph for that problem. Okay, lastly, here we have part D, that it says here to find the average value no, not average value, average rate of change, that is, of f on the interval -4 to x going to +3. Okay, it says here that there is no point c from -4 to c to +3 for which f prime of c is equal to that average rate of change. Okay, and then it says here that explain why this statement does not contradict MVT. All right, this is actually a little bit of a difference from what we normally answer, because usually we try to use MVT to prove a point, but now we're actually trying to say that it doesn't contradict it because there is no point C in which it will be equal to that. So first, let's have a look here that we have ourselves the average rate of change. So again, this is going to be from the interval from -4 to +3. So with that, we need to then go for f. So this means f of +3 minus f of -4 and the difference of those x values. Okay. So by doing that, we just need to refer back to the graph here. So it's -3 as f of 3 subtracted by -4 being -1 on the point there. And then 3 minus a -4 is going to be a +7. So with that, we get a -2 over a +7 of -3 minus a -1 from that. Okay. So this is going to be the average rate of change. Okay. But now they're showing that there can't be the f prime of c being equal to that -2 over 7. Okay. And they want to show us that this is going to be the case. All right. So for one, we know that f is continuous on the interval from -4 to +3, but we can see that if you actually look at the graph of f, right, you can see that even though it is one continuous function, we have a problem here at x is equal to 0, right? It is actually it is not differentiable because it is a corner of two separate functions that changes from that circular one down to a straight line. Okay, so even though f is continuous, it shows that f is not differentiable on x is equal to 0, right? That is the key here because the mean value theorem, right, MVT requires f to be continuous and differentiable. Right, differentiable on the interval from -4 all the way to +3. Okay, right. Yeah, to work, I guess. I don't know, but yeah, they just guarantee that f prime of c being equal to -2 over 7 exists. Okay, so we have our reasoning to show for that as well. Okay, that the full understanding of mean value theorem and what we are required to show for it, that it is both continuous on the interval as well as differentiable, but us having a problem of differentiating it at x is equal to 0 will then throw mean value theorem out of the way as something that cannot be used for this part. Okay, very good. So with that, we should have exactly what we need to then go and start correcting our work that we've done so far on problem number 3 first. Okay, so problem number 3 is saying that we need to do that line tangent equation of the function of f, which they gave out earlier. Okay, so by thus doing the point slope form of the 6th slope x minus 1/2 plus a 1 on the outside, that's exactly what they're looking for. Okay, and then of course taking that derivative function to then find the actual slope is also how we get there in the first place. So that will be 2 out of 2 correct for ourselves for part 3. Okay, and then for part B here, at least to find the area of R, okay, then yes, we need to set up that integral from going from 0 to 1/2 of g of x minus f of x by our work showing that g was indeed on top of f in terms of that region R. So that's one part that they're looking for. Then by actually running the integral of sine of pi x minus 8x to the third power, running that to actually get the -1 over pi coefficient multiplied by cosine of pi x minus 2x to the 4th. That's exactly what they needed to see, that we actually ran the integral properly. And then the final area itself of -1 over 8 plus 1 over pi was exactly the answer that they're looking for. So that will give us a total of 4 out of 4 points for part B. Okay, and then lastly for part C, by then showing that we can actually find that volume, and we need to show that the actual limits going from 0 to 1/2 that they're looking for. Okay, as well as that constant of pi. That, I guess that's important for them to actually give you a point on to make sure you understand how to do volume by keeping that pi coefficient out there. We need to then set up the integral of that 1 minus 8x to the third. Again, that was the f of x function on the one that was further away from the line that was being rotated about, all raised to the second power minus 1 minus sine pi x. So that was the g of x that was closer to the line that was being rotated on the axis, raised to the second power outside of that as well. Okay, so all of this is what they're looking for, at least to show that we can do the integration to find that volume if it was rotated about y is equal to 1, but actually not resulting in an answer because that's not what they were looking for on this part. But with that, that will be all 3 out of 3 correct for this part. That's quite exciting that this next one, question number 3, all 9 out of 9 points would be awarded to us as well. Okay, very good. So then going over to problem number 4 here, the one that did take us quite a little bit longer than we normally would have. Okay, so each of those parts, g of negative 3, was then solved by plugging the negative 3 and doing the actual integration. Okay, so actually finding the integration from the graph itself as the area underneath the graph of f, we end up with negative 6 minus 9 pi over 4. That's exactly what they wanted to see. Then the g prime resulting in 2 plus f of x, thanks to fundamental theorem of calculus. That was also correct. And lastly, by plugging it in, we get a positive 2 of g prime of negative 3 as well. That all shows that we know exactly what we're doing to find each of those different function values. Okay. Then going over to part B here, then we need to see if we are looking for that absolute maximum here. Okay. So we are looking at all the different ways in which we can get that. Okay. So we have all the candidates at the 5 over 2 being one of them as a local maximum. Okay. And then we also have the ones at the negative 4 and positive 3. It's very interesting. The answer key actually doesn't go so far into depth about looking for each of them. But in any case, though, by actually looking at all the candidates that we have so far, by proving mathematically that g of 5 over 2 was correct, that will indeed give us all the points that we need, because we did show that g of 5 over 2 is the absolute maximum after taking all of those integrals that we very painstakingly did, but was able to get the actual result from that. Okay. Yes, we have Mijinin telling us, what a trustable teacher. Yes, thank you very much for your support. We do look forward to what our viewers have to say about the way that we go about these types of free response questions. Okay, so with that, that was all of part B, again showing us exactly what we needed to do in order to prove that g of 5 over 2 was the absolute maximum for the function at that interval. Okay, so then we look at part C here, that we have the change of sign only at x is equal to 0. Again, that's what we showed that. Again, the first derivative of f being the relationship to the second derivative of g right there. So because of that, again, we're looking for the change in sign again between the two, right? So given that, we actually have ourselves the increasing, decreasing change of sign of f, again, of the first derivative of f. So that does prove that that was an inflection point for the graph of g because of that. Okay, so that should have been all. This was actually just a single point, 1 out of 1 correct for part C. Okay, and then lastly for part D here, we had to show that the averaged change by running it through again those 2 points for the endpoints of the interval from negative 4 to positive 3. By just simply plugging that into our equation, we do get the correct negative 2 over 7 as the averaged change of f on the interval. But it does show that, again, that the f is not differentiable on x is equal to 0 across the interval, right? So because of that, we do show the explanation that, again, that MVT cannot be used to guarantee that value of f prime of c being negative 2 over 7, because mean value theorem no longer holds up because we have points that are not differentiable on this function. So that is 2 out of 2 correct for us on that as well, by showing both the averaged change and the reason why MVT cannot be used here. So because of that, we actually do end up with, again, another total section of it being 9 out of 9 correct. Very good. So we are on the home stretch here to actually try to show that we can get all 54 points correct. So let's see if we can do that on these last two parts. I'd say this is quite exciting. We can try to make channel history over here with all that we've done so far. So let's go on back to question number 5 here as we look at what we have next for us. Okay. So with question number 5, again, it looks like they shoved in 5 and 6 together on this last page, but we'll just go over one at a time, and I will copy over question number 5. Okay. So let's see here. Okay. So question number 5 begins here with the bit of context that at the beginning, hey, come on, I need to write properly. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Okay, so then it says here that planners estimate that W will satisfy the differential equation dW over dt being equal to 1 over 25 multiplied by all of W minus 300 for the next 20 years. Okay, so W is in tons and T is in years from the year 2010. Okay, very good. So with that, we can go over to question A here, that it says that we need to use the line tangent to the graph of W at t is equal to 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. Okay, so then they, if they want to, they gives a hint that it's time being equal to 1 over 4 for that change of 3 months. Okay, so if we want the line tangent again of W at t equals 0, okay, that means that with the t is equal to, again, so that gives us that W of 0, that point that they gave us earlier at the start, is that it starts at 1,400 tons of waste at the landfill. Okay, but we need to actually use the line tangent, which means that we need to do dW over dt, so that derivative function, again, at the time is equal to 0, to then find that slope for us to construct that line tangent to the function. Okay, so with that, at time is equal to 0, so 1 over 25, the W that we started with was indeed 1,400 minus 300, which would be 1 over 25 multiplied by 1,100, and then dividing that by 25 should give us 44. Yeah, 44 as a result. Okay, and this is going to be tons per year. Okay, right, that will be stored into the landfill. Okay, so with that, again, this is going to be the actual slope of the line, and we have the point that W of 0 being 1400 as a result from that. Okay. So from there, we should be able to then construct this equation. So y is equal to the slope of 44 of x minus 0, and then plus the 1400 on the outside, as point slope form will show. Okay. So with that, again, we need to then approximate, again, t being equal to 1 over 4. Again, that, in this case, that's going to be x as well. I just change it to x just to show for at least what that will look like equation-wise. Okay, so by approximating the t is equal to 1/4, that means y is equal to 44 multiplied by 1 over 4 plus the 1400, which 1/4 of 44 will give us 11 plus 1400, which will be 1,411 tons. That will be the approximation of the amount of the waste that is put into the landfill at that time. Okay, pretty nice, as a very easy way of doing a tangent line approximation. Fairly straightforward. But then the next part is that we want to find dw, the second derivative of the waste respect to time, in terms of w. Okay, and so use that response of the second derivative of w over t, okay, to determine if part A's answer is an overestimate or underestimate. Okay, all right, at the time that part A was being asked about. All right, so because of that, we have to go take the next step here, that given that we are taking the dw dt function, which was the 1 over 25 multiplied by w minus 300, okay, we need to then take its second derivative by taking one more derivative in respect to time of that. So with that, what I personally like to do is to do a little bit of distributive property, just so that we know what we're looking at. So 300 divided by 25 means that we end up with a 12 as a result. Okay, so that will be distributive cross, but then we need to take its derivative again in respect to time because of that. And from there, we then end up with the dw over dt, again, that derivative function divided by 25 again, subtracted by 0, as 12 would just go straight to 0 from a derivative. Okay, and so we can just plug back in once more that from the second derivative, that we get the 1 over 25 as a coefficient, and we plug back in the entirety of dw over dt, like that again. Okay, so from there, we just have to do some last moments of putting everything together here as a nice function. So 25 squared, that should be a lovely 625 if we remember our scoring tables here. And then it's w. Okay, I think this should be fine enough to show that this is going to be the second derivative of w, done implicitly. Okay, but then we need to see if this was an over or underestimate as a result from what we had on part A. Okay, so because we were using the time is equal to 0 on that type of function, right? That means that the second derivative at time is equal to 0 is going to be the 1 over 625 multiplied by 1400 minus 300, okay, which will give us an 1100 over 625. Again, this is be concave up for the function of w. All right, so because we're going concave up, at least as well for a function that has been increasing, and given that the slope was a positive 44, so we can conclude the facts that we are concave up for function. Okay, so because of that, right, so if we want to take a look at that visually here again, right, concave up and increasing means that we're going to go something like this in that curvature going in that direction. But if we then take a tangent line as what we did on part A, right, so that's part A shown on the line that has been going straight as a tangent line, only touching on one point and going off there. Okay, that we are indeed going to be an underestimate of t is equal to 1/4 as a result of what we've concluded so far with the second derivative. Okay. So then we can go lastly to part C over here. It is asking for us to then find the particular solution W is equal to W of t to the differential equation dw over dt being equal to 1/25 u minus 300 with the point w0 being equal to 1400. All this was already expressed in the problem. It's just that now we need to find some actual solutions to this now that we have to do some good old separation of variables. Okay, so we can start with the dw over dt function being 1/25 w minus 300. Okay, so starting there, we need to then go evaluate this backwards back to the original function. So what we can do is that we can say it's dw over w minus 300 by moving that over to the left side, and the dt's need to be moved over to the right side. So 1/25 dt. Okay, so this should be fine actually now from here to integrate on both sides, as dw with the w's are on one side and the dt is left with the coefficient. That's completely fine to integrate all on its own. So by integrating the dw over w minus 300 and the integral of 1/25 dt, okay, which then we'll be able to find what this looks like on both sides, meaning that we get the natural log of w minus 300, which is perfectly fine to have as an integral result of 1/w minus 300 and 1/25 t plus c as a result. Okay, so again, that constant of coefficient, the constant of integration obviously came from doing indefinite integration on both sides of this problem. And so from that, we just need to go ahead and now plug in for, so I'm going to take a note, we need to plug in the w0 being equal to 1400. So with that, we get the natural log of 1400 minus 300 being equal to 1/25 t was 0 plus c, so we could then solve for c on its own, which in this case, everything works out quite nicely. That c is equal to the natural log of 1100 as the constant of integration. So because of that, we have the natural log of w minus 300 waiting for us is equal to 1/25 t plus the natural log of 1100. Okay, so now we need to take just these last steps here to isolate for w, such that we end up with the actual equation of wt that we need. So because of that, we just got to raise everything to the power of e to cancel out the natural log on that side, which will also cancel with the natural log on the constant right there. So we get w minus 300 being equal to e raised to the 1/25 times t plus, not plus, it's being multiplied now, so multiplied by 1100 as a constant on the outside, as the natural log canceled and moved back down as a coefficient. So with that, we end up with the final w of t, with that 300 being moved over to the right side, of 1100 multiplied by e raised to the 1/25 t plus 300. And that should about do it for that problem. Okay, so very classic separation of variables, something that should be easily done by most calculus students by them knowing how to move across the dw and dt so that all the variables of w on one side and the variables of t on the other. Okay, let's go on to the last problem, 6, and we shall see if we have indeed broken our record for our first perfect score exam. Okay, so part 6 says that we must let f be a function defined by the following of f of x being equal to the piecewise function now of 1 minus 2 times sine x on the top and e raised to the negative 4x on the bottom. And so the top rule is for x being less than or equal to 0 and the bottom being for x is greater than 0. Okay, so we have all of that listed out there. Okay, so let's see if part A is asking that we want to show that f is continuous at x is equal to 0. Okay. Fairly straightforward on this part, that we need to do a continuity test here. Okay. So if you want to make sure that it's continuous, we have a couple of points that we need to conclude, right? First off is that we need to take the limit as x approaches 0 on both the right side of f, and that the limit as x approaches 0 on the left side of x are going to be equal to each other. And then on top of that, if we can prove that, then the limit on x approaches both sides of the function must be equal to the original point f of 0. We have those two steps that are laid out for us as the actual steps needed to prove continuity on a single point for a function. So let's go right on ahead and start doing that. Okay, so with the limit as x approaches 0 on the right side of the function of f, that means we're going to pay attention as x is greater than 0 on that bottom rule. Again, we're pushing on the right side of 0 coming in from positive numbers, meaning that we take the function of e raised to the negative 4 and we plug in the 0 as the limit approaches from that rule. So because of that, that will be e raised to the 0, giving us a positive 1. Okay, fairly straightforward there. So let's see how that compares if we took the limit as x approaches 0 on the left side of that same function. So in this case, we're going to now follow the bottom rule as that will include all values below the actual point of 0. So because of that, that'll be 1 minus 2 multiplied by the sign of 0 as we plug that one in. Okay, so 2 times sine of 0 is going to be just simply 0 as a result of us understanding the unit circle, giving us a positive 1 as well. So those seem to both work out very nicely, which means that then if we then plug in lastly for the original function f of 0, the actual defined point for this function, that then means we need to evaluate still on the top rule because that includes the actual point of 0, as it says that it's for f being less than or equal to 0. So because of that, we then just plug back into the top rule, so 2 times sine of 0, which we've already evaluated earlier, which nicely ends up as 1. Okay, so both of these check out with all the work showing for both the point and the limit as x approaches 0 on both sides, on the left and right side of that function. So therefore, the function is continuous at let's just do the problem set x is equal to 0. Okay, again, we have shown that the limit as x approaches 0 on both sides of the function is equal to f of 0. We've done that part through and through with all of our work that we've shown so far. Okay, so let's go over to part B here. It says that for x being not equal to 0, express f prime of x as a piecewise defined function. Okay, and then it says find the value of x for which f prime of x is equal to negative 3. Okay, so there you go. All right, so from here they said they're looking for a specific piecewise defined function that it's not going to be equal to 0. Okay, as we find the f prime of x. Okay, and then we need to find that exact point where f prime of x is equal to negative 3. Okay, so if we want to do f prime of x, that just means that we have to do then for both parts here, okay, that we go for both the top and the bottom rule. So for the 1 minus 2 times sine of x, if we took the derivative in respect to x one time for that top rule, that means that 1 goes to 0, so it's negative 2 left out there as the cosine of x as a result of that. Okay, again, this is where for x being less than 0, we can't include 0 because that is a corner between parts of the function, which will not be allowed as we have seen on question number 4. So let's go ahead and go with the next part of the rule of e to the negative 4x. So let's take this guy's first derivative, which then we just bring down that negative 4 as a result of the exponential rule. We leave everything else intact for this guy, and that will be the next part of this function. Okay, and this is now for x being greater than 0. Again, we're not including 0 because that is a change of 2 different parts of the function. Okay, so then it says we need to find the value for which the f prime of x is equal to -3. Okay, so something to note here that we can do here is that that we can try to take a look as to what this needs to be in terms of this part. Okay, so if you have -2 times cosine of x, right, could we ever have an x where it's equal to -3? Right, we need to just a little bit of analysis here to understand that cosine of x, right, this guy entirely, right, that cosine of x only ranges as a trigonometric function from -1 to +1, right, as a result of that. So even if we multiply that by -2 as a range from -1 to +1, again, we will never be equal to -3 no matter what the x is. Okay, so all of those values are no good for the top part of the function. So then we can try to see if that matches for -4 e raised to -4x. Can that be any point be equal to -3? Okay, so with that, we can then just go ahead and try to see here that we have e raised to -4x. We divide the -4, so it's 3/4 in the positive sense. Then we take the natural log on both sides, so that the natural log of e is going to cancel, so that's going to be a -4x being equal to the natural log of 3/4. So then x being equal to the natural log of 3/4 all over -4 will indeed be the proper way to get that result on the first derivative of x being equal to -3. Okay, very nice. So we've shown both the piecewise function that will show for the result of this, as well as the actual x value that is needed. Okay, and with that, yeah, something that we might need to note here is that with the natural log of 3/4, again, given that then the 3/4 is less than 0, again, this will give us the natural log of 3/4 giving a negative number here too, right? In other ways, we can also show that the natural log of 4/3, so good, some very nice usage of negative exponents with logarithms, will then actually cancel that out if we wanted to show it in a nicer way of the natural log of 4/3 canceling with the negative of +4. That would work as well to show that we are indeed above 0 for us to follow that rule that was expressed on that piecewise function. Okay, let's go to the very last section here on part C, that we want to find the average value of f on the interval -1 to +1. Okay, so average value of f, well, that's just going to be that we're going to have to take the coefficient of 1 over the 1 minus -1 for the integral going from -1 to +1 f of x dx. A very simple setup for the average value equation there, which for us will be giving us 1/2. Now, because we are going from -1 to +1, we are crossing over two different parts of that function that was described because it splits right at 0. So because of that, we would need to then split this up from going from -1 to 0 for the function of f, and adding that now between the two of them from 0 to +1 f of x dx. Right? This split is going to be necessary for us to follow all the rules to make sure we're integrating for each part of the function, as again they split at 0, so the functions will be split accordingly. Okay, so with that, we have the 1f coefficient. Then we need to plug in each of the rules from -1 to 0. That's going to follow the top rule of 1 minus 2 times sine of x dx. Okay, and then we need to add that with the second part of the rule going from 0 to 1 for e raised to the -4x dx. Okay, so with that, this is how we're going to go and find that average value. So let's go and leave that coefficient there, and let's see what this integration turns out to be. So 1 minus 2 sine of x is going to be x multiplied by, well, added with the +2 times the cosine of x, because cosine will give us back to negative sign if we ran that differentiation again. Now divided from -1 to 0. And then we need to add that with now the second part of e to the -4x. That integral is going to be e to the -4x still, but because the coefficient -4 would be coming down from that derivative, we take a negative 1 over 4 coefficient to counteract that, evaluated from 0 to positive 1. Okay. A little bit squished in there, but I think we should have everything we need to start putting this through. So with that 1/2 positive coefficient, we then need to evaluate from 0 to negative 1 for the first integral, which will give us the total of 0 plus 2 times the cosine of 0. Okay. And then we need to subtract that with, interesting. Okay. Well, subtract that still with the, we have a negative 1 plus all of 2 times the cosine of negative 1. Okay. And then we need to add that then with the second part of the integral of negative 1 over 4 e raised to the negative 4 power, and then subtract that with that negative 1 over 4 coefficient still of e to the 0 power. Okay. So with that then, we can go and put these last pieces here together, and we should be well on our way through. So with that 1 over 2 coefficient, and cosine of 0 is going to be given us as a positive 1. So that's going to be a positive 2. And then subtracted by negative 1 would be plus 1, and subtracted by a 2 times the cosine of negative 1. So we don't really need to evaluate that since this is a no calculator section. So we can just leave it as such like that without a problem. And we'll see to where we can go with the rest of that. So we have that negative 1/4 e to the negative 4. And then the e to the 0 gives us a positive 1. So that will give us a positive 1/4 as a result of all of those coefficients canceling out. Okay. So with that, we end up with a positive 3 and a positive 1 over 4. So that should give us now, that'll be 12 over 4. That gets put there. So 13 over 4 with another 1/4, so it'll be 13 over 8 as the first part of this. And then we just need to keep that subtracting 1 over 8 e to the negative 4 subtracted by a 2 times the cosine of negative 1. Okay. The 1/2 coefficient will make it a positive 1. There you go. Okay. And that should be the average value. A little bit messy, at least in terms of getting this to be all turned into one exact equation. But that should be exactly what we need here. If you followed every step here to get the average value along the interval that they're talking about. Okay. So hopefully we shall see what this looks like in terms of all of that we've looked into for this part. And we shall do our final corrections here to take a look to see if we have indeed gotten the highest score that we can for this exam. Okay. So getting back to problem number 5, again, we have that landfill problem. So first off, by doing the actual tangent line approximation, we ran the derivative at time is equal to 0. Okay, so with the derivative equation they gave us, we just plugged in for the waste at the time of 0. So by running it through, we do end up with the equation. And by running it through, yeah, we showed that we got the result of 44 tons per year as the slope of that line. So we plugged it into 44 times that 1/4 plus the 1400, which would give us 1,411 tons, which is what they were looking for us to confirm at the start. So with both of those showing there, that's 2 out of 2 correct for part A. Then for part B, we need to then take that second derivative in respect to time for this guy. Okay, so by running that through, we do end up with the 1 over 625 of w minus 300 as the rate showing of the second derivative of that equation. Okay, all right, keeping everything in terms of dw over dt that was needed to be done in terms of the actual problem itself. So that's the first part that they're looking for. And now the second part, given that we are concave up, again, showing that it was greater than 0 for that point in which we were looking at in terms of that tangent line approximation. Okay, and this is going to be indeed an underestimate of the actual value of the function. Okay, so that will be 2 out of 2 correct to display that properly. Over to part C here, again with the separation of variables that needed to happen. Okay, so yes, we need to separate it with the dw, w minus 300 on one side, and then 1 over 25 dt on the other side, so we can actually run the integral on both sides. So with that resulting of the w minus 300 in the natural log and the 1 over 25t plus, extremely important for us because we actually need to go solve for that with the w of 0 being equal to 1400 at that part. So because of that, we use that initial condition, run, and we get our constant being equal to the natural log of 1100. So plugging that back in, we can then solve lastly for the w of t on its own, with that natural log of 1100 becoming a coefficient after coming out of the exponent spot. So wt being 1100e raised to the 1 over 25t plus the 300 at the end was indeed going to be the right way to show for the waste function. Okay, so all of that through is indeed going to be correct to give us all 5 out of 5 correct for this part. Okay, and with that, that also shows that what they would point out for the grading section of this as well is that if there is no plus c that you showed in your work, you could only get a maximum of 2 out of 5 points. That's something that they explicitly point out in the grading section of this. And then going back to this as well, if there was no separation of variables, so if we did not take the step to move over the w's to one side and the coefficient to the other to keep it away from each other to actually run the integral, you would get 0 out of 5. So that's a pretty big hit for the students who don't think it's necessary to do that, but it absolutely is if we are looking to integrate this properly and get the right answer that they were looking for. So because all that was shown properly, we get 9 out of 9 correct for this part, and that will give us 9 out of 9 out of question 5. All right, we are on the home stretch here. Let's see if we can actually get all the parts correct on this last question, and if we can break our record for this first time we do this. Okay, so question 6 is going to be starting with the analysis of that piecewise function right there of the two-part split at x is equal to 0. So we can show the continuity that we want to take the limits on both sides of the function approaching 0. So because of that, they are both indeed equal to 0 on both sides, and the point as well matches accordingly. So we can conclude that it is continuous with the value of 1 showing up across all the different values there. So that's 2 out of 2 correct for us on that part. Okay. Then for part B, then we need to show that we can take the derivative. So that's going to be the negative 2 times cosine of x and negative 4e raised to the negative 4x as a result of that part. That's exactly what they're looking for. Then to find the actual value of x, yep, they left it as the negative value there. So by just then understanding that this top rule of negative 2 times cosine of x can never be equal to negative 3 because of the limitations cosine has, then we look at the next rule of the negative 4e raised to negative 4x to set that equal to negative 3 as the result of the derivative. Then by running it through and separating everything out, we do get the final answer of x being equal to negative 104 multiplied by the natural log of 304, again shown exactly there. So that will be all 3 out of 3 correct for both showing the derivative and the possible x value to match that result that they're looking for. Okay, then lastly, we actually have this last part here in which they were looking to do the average value of the function of f from negative 1 to positive 1. So because of that, we did have to split up the integral because we were going across 2 different function values because of that at x is equal to 0. So that's what they wanted to see, that we understood that one rule affected it on one integral and we had to split it for the other rule on the other integral. Okay, so by running the actual derivatives on the integral, on both sides, and by plugging in the rules, we do end up with the x plus 2 times cosine of x on one of them, and the negative 1 over 4e raised to the negative 4x as shown right there on the other side as well. Okay, and then we evaluate it accordingly. So we end up with that 3 minus the negative 2 times cosine of negative 1, and the negative 1 over 4e raised to the negative 4 plus the 1 over 4. Okay, then by slapping on that 1/2 coefficient across all of them, we do get the whole 13 over 8 minus 1 over 8e to -4, and then minus, that's a 1 right there. That was the whole 1 cosine of -1, because that -2 added with multiplied by the 1/2 will give us a whole 1 coefficient. So that does conclude that all 4 to 4 were correct as well on this part. And looks like we indeed finally have on the 2011 AP Calculus packet that all 6 questions were answered on full points. Well, that is quite something. I think this is really nice to hold on to, as this is all will be recorded and held onto the channel itself as one of the live recordings, that we have indeed gone through all the steps required to get exactly full points across this entire packet. Okay, I think that quite sums it up very nicely. Again, we'll be looking through additional packets as we move along. Again, the actual exam, if we take a look here, let me make sure we're on. Let's see. Yeah, 25. Okay. Yes, it should be May 12th. Let me double check and make sure we're on this. Yeah. Yep. So on May 12th, which is going to be exactly 1 month and just a few more days away, this should be a nice cornerstone, at least for what we've done so far on this channel, as going through the free response packets. So in other channel news, we'll be looking through, in terms of the next video, I'm actually going to be working on the next biggest upload, which will be hopefully an entire run through of all that needs to be studied on this exam, so that students can actually look through this and run through every chapter and every unit, so that they should be prepared to take that exam coming up in exactly 1 month and a few days. Okay, I think that'll about do it for now. Again, we'll be back here on Thursday at the same time, 4 p.m. Pacific time, for us to go over another packet and to see if there are any other questions from our viewers. Again, I do see that we do get a few more views after the live stream is over, so hopefully this should be good enough for any other students coming in to see how these problems are done, and we should be back again on Thursday. So we thank you all for tuning in, and we'll be back again in a couple of days for another packet. We'll see you then.